In this lesson, we're going to take a look at the 6 trigonometric functions. So to start off, we need to understand that trigonometry is related to similar figures in geometry. Similar triangles are triangles that have congruent angles and proportional size. You may remember that from geometry. One way that we can prove that two triangles are similar, if we have two angles that are congruent to two angles of another. We call that angle-angle similarity. So here we have two triangles. They both have a 90 degree and a 22 degrees. 90 degrees and 22 degrees. So these two triangles should be similar. They are similar, in fact. Similar means they are proportional. Their sides are proportional and their angles are equal. So are these two similar? Yeah, they are. Okay, they're similar by angle-angle similarity. All right, that is one of those theorems from geometry. All right, angle-angle similarity is that theorem. All right, so we know that they're similar. So since they're similar, their sides are supposed to be proportional. So since they're proportional, we can find the value of x. So x is a hypotenuse here, and we know this leg over here. Over here, we know the hypotenuse and the leg. Now, there's lots of ways to write this proportion, but let's try this. Let's compare a leg and a hypotenuse, because over here we got 3:8. That's the ratio of a leg and a hypotenuse. Well, 3 is this leg that's on the 90-degree angle, okay? That is connected to the hypotenuse, so between the 90 and the unknown. So 4 is this one over here, so 3 corresponds to 4. So 4's got to go on top and x has got to go on bottom. Remember how to solve a proportion? Thinking way back, well, we can cross multiply, right? So if we cross multiply and rewrite, 3 times x equals 8 times 4. And that shouldn't be too tough to solve. So we have 3x is 32, divide by 3. Excuse me, x is 32 thirds. Or if you really want, it's about 10 2/3 exactly. All right. So either answer is fine, preferably the fraction actually. So we know that this is 10 2/3 or 32 thirds. All right. Now the question is, could we do the same for y and z? And we could. We could use actually the Pythagorean theorem here to find y. But let's think about some other proportions here. Let's use the names of the sides to complete this proportion. We've got BC is to AC. Well, BC is over here. AC is that hypotenuse. Well, that's equal to, should be the corresponding sides over here. BC is on top, corresponds to FE over here. And AC is the hypotenuse, and that's equal to DF over here. All right? So that proportion always has to be true, no matter what the numbers are. Well, let's see if we can write some other proportions. Try pausing the video and write some other proportions using two sides from one triangle and two sides from the other. So make these two over here come from one triangle and these two come from the right triangle. See how many proportions you can get and then come back and take a look. We could take AB over AC, that's this bottom one over that hypotenuse, and that'd be the same as ED over DF. Let's see another one. We could take this CB, the short leg, over the long leg. That gives us CB over AB, and that should correspond to these two over there. So they're proportional because they're similar. So EF is to ED. All right, so we have those are the legs. So here we had a leg and a hypotenuse, leg and a hypotenuse. This was a leg and a hypotenuse, leg and a hypotenuse. These are two legs over two legs. They're in the right order, small over large. What else? Well, we could also flip this, right? So we could take AC, the hypotenuse, and put it over BC. That's one proportion, or one fraction from this, that's hypotenuse over that leg. Well, that would be this hypotenuse here, DF over EF. So we have DF over EF there. That's the hypotenuse over that leg. We could take the hypotenuse over the long leg. That's another one. Like AC over AB, that's one proportion from the left side. We could take the hypotenuse over the long leg over here. And there's another proportion that must be true. We're looking for one more here. Well, we had CB over AB. That's short leg over long leg. Let's flip that around. Let's make that AB over CB. All right, AB over CB. And what does that equal to on the other side? That's going to be equal to ED over EF, or FE. All right, so here we have 6 total proportions. All these proportions must be true. So if we have 2 triangles and we know that they're similar, these things must be true. All right, and we have some names for this. If we think about all their relation to this angle 22, this relationship here is the sine relationship of 22. It has to do with the opposite over the hypotenuse. This relationship here, that ratio here, we call the cosine. This one here, we're going to call the tangent. That's a ratio of the two legs. This one over here, we flipped AC over BC. Well, that's going to be called the cosecant. And here, we flipped over the other one, we said what? AC over AB. That's going to be called the secant of 22, all talking about the 22. And this guy's going to be called the cotangent. So the idea I want you to get here is that we've got these 6 proportions. They're always true no matter what, because the triangles are similar. And that's where trigonometry comes from similar triangles, all right? And so when we have a right triangle and we have some angle theta like that 22, we're going to define the sine to be the ratio of this opposite leg, opposite meaning it's all the way on the other side. So it's opposite. The opposite leg over the hypotenuse, that's a sine. Cosine is going to be the adjacent leg over the hypotenuse. Whatever that length is, the tangent is the opposite over adjacent. You're probably familiar with those from geometry. Some new ones, though, we're going to flip them around. Sometimes we want to put the hypotenuse on top of the opposite. That's going to be called the cosecant. The hypotenuse over the adjacent is the secant. The adjacent over the opposite, just flipping this around, gives us cotangent. Okay? So there's our definitions of our trig relationships, trig formulas. Okay? And so we want to find these values of a given angle. Here we have an angle. I don't know what it is. It's theta. It's unknown. I think we can find x, though, because it's a right triangle. So let's try some Pythagorean theorem. We know 4 squared plus 5 squared equals x squared. Is it a 3, 4, 5 right triangle? Not quite, because x is the hypotenuse. So that's going to be 41. And if we square root that thing, we get the square root of 41 equals x. So x is the square root of 41. All right? So let's find the value of the 6 trig functions here for this angle. We have the sine, cosine, and tangent. Now, again, we don't know how big the angle is, but that's okay, because we know by the definition above that the sine is the opposite over the hypotenuse. And so that is, well, what's opposite of this angle theta? This is the opposite side. And the length of the opposite side is 4. The hypotenuse is the square root of 41. We're not going to worry about rationalizing the denominator right now. Okay? The cosine, well, cosine of theta is adjacent over hypotenuse. And adjacent, well, the adjacent is the leg. That's the adjacent leg. It's connected to the angle that we're talking about. This is theta. That's the angle we're talking about. That is the leg that's connected. It's called adjacent. So that's 5 over 4. And then last but not least, the tangent of theta. That is opposite over adjacent. So starting at the angle, opposite is 4, adjacent is 5. All right? So 4 over 5. Now we're just going to flip those around for our new functions here. For cosecant, which we described a minute ago, that's hypotenuse over opposite. Well, that's going to be square root of 41 over 4. The secant is the reciprocal of cosine. That's going to be hypotenuse over adjacent. And that's going to be 4 over 5. And, oh, what happened here? Oh, did you catch my mistake? That's pretty bad news. Let's come back. The cosine. Man, going too fast here. Cosine is the adjacent over the hypotenuse. For shame. That's 5 over the hypotenuse, which is square root of 41. You've been shaking your head this whole time saying, wait a minute. So let's fix that. That's the square root of 41. Shame on me. So flipping that around, the hypotenuse is the square root of 41. Don't go too fast, right? All right, square root of 41 over 5. And last but not least, the cotangent of theta is adjacent over opposite. And adjacent over the opposite, well, let's look back at our angle. The adjacent is 5, and the opposite is 4. So that's going to give us 5 over 4. And we notice that it's just the tangent flipped. All right? So there we have those answers there. There's our tangent. There's our cotangent. Over here, now that we fixed that mess there, we have our cosine and our secant. And we have our sine. And flip it over, we have our cosecant. All right. Well, how about this? What if we know the tangent of a triangle, or an angle specifically, and we want to find the other 5 trig functions here? Well, we're told that the tangent of an angle here is 5/7. What is tangent? Well, by definition, tangent is opposite over adjacent. Okay, so if that's opposite over adjacent, then that's 5/7. That tells us something about our triangle. And we can draw a triangle here. Let's get a little straighter line there. Okay. And so if this is theta, the opposite leg, we're saying, the opposite leg is 5. So this guy over here is 5. The adjacent is 7. And I don't know what the hypotenuse is, but I bet we can figure it out. And we're going to want to do that. So let's go ahead and figure that out. 5 squared plus 7 squared equals c squared. So 25. 5 squared is 25. 7 squared, 49. Add them up, we get 74. So 74 is c squared. Let's square root that. And we get c is the square root of 74. Let's see, does 4 go into there? Actually, no, it doesn't. So no 4s, and there's no perfect squares. 36 doesn't go in there, so nope. All right, can't simplify it. C is the square root of 74. All right, so with that triangle, let's see if we can find the sine of theta, the cosine of theta, the tangent of theta, and then their reciprocals, the cosecant of theta, the secant of theta, and the cotangent of theta. So pause the video real quickly, see if you can find those. Just write the fractions, and then come back and we'll see if we agree. All right, so sine is opposite over hypotenuse, should be 5 over the square root of 74. Cosine is adjacent over hypotenuse, 7 over the square root of 74. Tangent is opposite over adjacent, that's 5 over 7. Remember, it all comes from this angle. This is the opposite because it's opposite of the angle that we're talking about. The cosecant here, that's going to be the reciprocal. We're just going to flip these around. So we've got the square root of 74 over 5, square root of 74 over 7, and 7 over 5. Because if we look up above, these are called the reciprocal functions. Okay, cotangent is adjacent over hypotenuse, 7 over 5. Secant is adjacent over, I said that wrong, sorry. Cotangent is adjacent over opposite. Secant is adjacent over hypotenuse, so on and so forth. So if we have the sides, we can find the sine, cosine, and tangent. We don't need the angle. Now, this semester, we're going to be talking about this a little more generically, okay? And we want to know the relationship between these functions. We want to really get into the functions so we can generalize them and prove some interesting things about them. So to start off here, let's just think about which ones are reciprocals, okay? Which ratios are reciprocally? I guess we should have reciprocals. You gotta love spell check. All right, auto spell, I guess, autocorrect there. So which ones are reciprocals? Well, we know that sine and theta, sine of theta and cosecant of theta, they are reciprocals. Cosine of theta is the reciprocal of secant. And these pairings are real important. And if we just look up top, sine here is opposite over hypotenuse. Flip around, you get cosecant. Cosine and secant are reciprocal. Same thing with tangent and cotangents. So these relationships are real important between these pairs, and we'll use them a lot. Tangent of theta and cotangent of theta are reciprocals, okay? Now we're going to take, we can take combinations of functions and rewrite them. Let's take sine theta over cosine theta. What is that going to be equal to? If I take the sine and I divide it by the cosine. Well, if we use the definitions, we can say this. The sine of theta over the cosine of theta. Let's use a definition. Sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. Now, we want to clean this up. We've got a compound fraction. We got hypotenuse on the denominator there and hypotenuse on the denominator here. So let's try multiplying top and bottom by hypotenuse, just treating these like numbers, because they are. Okay? Multiply top and bottom by hypotenuse. Here the hypotenuse cancels. Here hypotenuse cancels. And we can do that because it's a fraction, as long as we multiply top and bottom by the same. And so we got opposite over adjacent. And what is opposite over adjacent equal to? Well, that's looking up at our definitions. That's just tangent. So sine over cosine, sine divided by cosine, is the same thing as tangent. That's kind of interesting. Well, what if we have cosecant over cotangent? Let's try that one. Cosecant over cotangent. So cosecant over cotangent. Cosecant, well, let's look up at our definition. Cosecant is hypotenuse over opposite. Cotangent is adjacent over opposite. So hypotenuse over opposite. Hypotenuse over opposite. And cotangent, we said, is adjacent over opposite. Again, we got this compound fraction. We got opposite on the bottom up here and opposite on the bottom down here. We would like these denominators to go away. So we want something to wipe them out, so we're going to multiply by opposite on top and opposite on bottom. Really, we're multiplying by 1. These cancel out, leaving adjacent on the bottom. These cancel out, leaving hypotenuse on top. So hypotenuse over adjacent. What is hypotenuse over adjacent? Well, if we look back at our definitions, hypotenuse over adjacent is the secant right here. So this is equal to secant of theta. And so now we can take some combinations of two functions and simplify them and write them as one. Okay? Last little thought here. Which trig function must be less than 1? Well, we know the hypotenuse is always the greatest. So hypotenuse is always the biggest one here, biggest number. So if we look here, the hypotenuse is on the bottom here. So this is always going to be less than 1 because opposite is bigger than, or less than the hypotenuse. Cosine is always going to be less than 1 because the hypotenuse is largest here. Tangent, we don't know which one is largest. But sine and cosine will always be less than 1. So which ones will be less than 1? Well, that will be sine and cosine. That'll be less than 1. Cosine of theta will always be less than 1. Well, what's going to be greater than 1? Well, hypotenuse is largest, so cosecant is going to be greater than 1 because hypotenuse is bigger than opposite. Secant is going to be greater than 1. It's hypotenuse over adjacent. So that would be the secant and the cosecant. So the cosecant of theta will always be greater than 1, and the secant of theta will always be greater than 1. All right? So there's a little introduction to the 6 trig ratios, and we'll leave it at that, and we'll use that to explore all kinds of things in this unit and get some really interesting results as we do trigonometry in an algebraic kind of way.